Hi, and welcome to Module 5 of Lecture 3. This is the last module in Lecture 3. This is a problem session module. We're just going to go pretty quickly through one more example of a multiple regression to get a sense for how they work and to give you more practice in interpreting the results. Okay, so this could be another vote choice example. So some random unnamed candidate. This is all imaginary data. Let's say we sampled 1,000 individuals out of some population at random about their choice for vote for a particular candidate. Call this person candidate A. And we asked also a bunch of individual questions about various characteristics of each respondent, and we did put them in, 3 of them, into a regression, and our regression looks like this. We have a constant, and our constant was 30, and our standard error on the constant was 22.7, and we measured the education level of each respondent, and we got 0.96 for the coefficient education level, and the standard error was 0.32, and we measured the income, and the coefficient we obtained in our multiple regression was 0.05 with a standard error of 0.2. And finally, we asked everyone if they had drunk milk that morning. And it's a dummy variable, 1 if they had drunk milk, 0 otherwise. And we get 15.6 for our value with a standard error of 3.12. Okay, so there you go. So we measured individuals' education level, their income in in thousands of dollars rather, their education level, and if they had drunk milk that morning. We put them all into a multiple regression, and we used that to predict the vote choice of the chance of voting for candidate A. Okay. So, first question, how many hypotheses are we testing? How many null hypotheses are we testing, and what are they? Well, the constant doesn't test any variation. It's just these 3. So there are 3 null hypotheses. The first one says increasing education has no effect on an individual's likelihood of voting for candidate A. The second one says increasing income has no effect on a respondent's likelihood of voting for candidate A, at least self-reported vote. And the third one says having drunk milk that morning has no effect on a person's likelihood of voting for candidate A. So there are 3 null hypotheses. When we do the regression, we get these estimates. What does that mean? Well, for each year in education, because we're measuring education in years here, for each year of education you have, you increase your chance of voting for A by 0.96. That's what this means. Income means for each $1,000 you make in income, you increase your chance of voting for the candidate A by 0.05. And milk means if you had drunk milk that morning, you would increase your chance of voting for A by 15.6%. That's what they all individually mean. Note that their meaning is tied both to the coefficients, but also to the way we measure each of these things. Income here is measured in thousands of dollars, so for each 1,000, you increase your chance of voting by 0.05, and so on. Okay, next up, t-statistics. Calculate them for each one. Well, all we have to do is take our coefficients, which are in the first column, and divide by our standard errors in the second column, and we get our t-statistic. So we ignore the constant. This one is 0.96 divided by 0.32, and surprisingly, it's a whole number. It's 3. Income is 0.05 divided by 0.2. So 0.05 divided by 0.2 equals 0.25, about a quarter, or exactly a quarter. Milk is 15.6 divided by 3.12, and that's 5. So we have t-statistics for each one of our 3 independent variables. What are our critical values? Well, we have n equals 1,000. There are 1, 2, 3, 4 parameters, including the constant. So our degrees of freedom equals n minus k, or 996. Given that size, even though it's a t-test, it's indistinguishable from the normal distribution, and the critical value there is 1.96 for a two-tailed test. We have no theoretical hypotheses indicating a one-tailed test here, so we just have a two-tailed test. So whenever the t-value is greater than the critical value, we say with 95% confidence that we can reject the null hypothesis associated with that independent variable. Remember here that the really nice thing about multiple regression is we're treating each independent variable independently. We can test each independent variable and its effect separately from the others. And I should have been more clear earlier on. When I said education, for each unit education, each additional year of education, you increase the chance of voting for A by 0.96. That's holding constant income and milk consumption. Similarly, when I said drinking milk that morning increases your chance of voting for A by 15.6, that's holding constant education and income. Holding constant those two things is key, and I really should have mentioned it first, but I'll mention it now. Holding them constant is key, and it's definitely part of the definition of how education affects chance of voting and so on. So we do these separately, and we get that this is significant, and this is significant, so education is significant, and milk is significant. Both are significant predictors of vote choice. Income is not at the 95% confidence level. Okay, now we'll conclude here with a prediction. So what if we had 10 years of education, and we had a person making $40,000 a year who had drunk milk? What's our prediction for the chance of voting for A? Well, our prediction here is y hat. In general, it's going to be the estimate of the constant plus the estimate of coefficient for variable 1 times some value for that variable, plus same for 2 times that variable, plus same for 3 times that variable. So now we have 30 plus 0.96 times, that's the coefficient for x, holding everything else constant, times the value of education, which we have 10. Then we're going to add 0.05 times this variable, which is 40. And then we're going to add 15.6, and this is a dummy variable for milk, so it's 1 or 0, and this gets to 1. So we add those all together, and we get 57.2. So a person with 10 years of education, making $40,000 a year, who drank milk, would have a 57.2% chance of voting for candidate A. This example is obviously ridiculous. Milk does not sway elections that they know of. Well, I guess no one's really studied that fully. Anyway, we don't think it sways elections. However, all that said, this is all we're doing here. The key is we have multiple independent variables we think affect the dependent variable. We include them in the multiple regression. We run the multiple regression. We return the coefficients and standard errors. Remember, this is not some kind of magic mystery. We did this in the matrix video. All these betas are the outcome of this particular equation. X transpose X inverse, X transpose Y. I say that fast because I've had to do this thousands of times in various classes. This is just what you do if you want to calculate the beta. This thing will equal your coefficient of beta. Your beta coefficient, your estimate of beta. So I should put an estimate, I guess, sign over there to be totally accurate. Okay, so this is your estimate of beta. There's nothing magical about this. Usually you don't do it yourself because inverting 1,000, well, in this case it's a 4 by 1,000. There's a 1,000 by 4 matrix. So it's a 4 by 4 matrix. Multiplying it is not trivial. Inverting a 4 by 4 matrix takes a lot of time. So you don't want to do this yourself by hand, but all sorts of statistical programs just run through this for you, and they produce a coefficient. It's not magic. The nice thing is that those coefficients, as we discussed at length in the first module in this course, tell you the rate of change of the dependent variable in the independent variable, with the independent variable holding everything else constant. Everything else here are the other variables you included in your regression. And you can predict values on y based on values of the independent variables and the coefficient that you estimated with your regression. That's it. That's all we have here. That ends module 3, lecture 3. In the next and final lecture, we're discussing some variations on regression that occur when you have different situations than the sort of norm, not norm, I guess, than what we've discussed so far involving mostly usual numbers. Thank you very much.